Right, check this out. I'm full of some chicken madras, and what that means is that I'm going to tell you a little bit more about what you can do with matrices. So check this out. The first thing is I don't really know how important this is going to be. The book goes clear. The book goes into this a little bit, so whatever. I might as well do this. But you can have matrix equations. Okay, what are matrix equations? Well, it's kind of like, a linear equation, but instead of dealing with, unknowns that are numbers, you can deal with unknowns that are matrices. So, for example, let's suppose that I'm looking at something like this. I want to know, okay, let's solve the following equation. I want to know if I take A, B, C, D, and I add that to the matrix 5, 2, 7, -1. Well, what do A, B, C, and D have to be in order for me to get the matrix 3, 8, 2, 5? Okay, well, maybe you can guess what you would have to do, but it's just like taking a linear equation and trying to isolate the unknowns. Here my unknowns are A, B, C, and D. I want to get them all alone. So I will just subtract this matrix to the right hand side. I'll subtract both sides by 5, 2, 7, -1, and that's subtracting by 5, 2, 7, -1. And just to make our life a little bit easier, subtracting is the same as adding by the negative. So I'll change that into a plus and put the minuses on the inside, and this minus becomes a plus. And so that tells me that A, B, C, D is equal to 3 minus 5 gives me -2. 8 minus 2 gives me 6. 2 minus 7 gives me -5. And 5 plus 1 gives me 6. And so that gives me specific values. A is equal to -2. B is equal to 6. C is equal to -5. And D is equal to 6. Fantastic. And you can go ahead and check that when you plug these values in, you get the right things. Now, why bother, though, writing an entire matrix as A, B, C, D, whatever? You could just call it some unknown x, and we can just think of it as the capital letter X. If you want to make sure that you know it's the capital letter X, you could put, like, serif on it or something like that. So it might even be easier just to do an example like this. If you want to know, if you want to solve a matrix equation, why not something like this? Let's do a column matrix. So x plus 0, 1, -4 is equal to 2, 3, 5. And so I will subtract this matrix from both sides. So x plus 0, 1, -4. I'm going to subtract from both sides 0, 1, -4. And that's equal to 2, 3, 5. And that 3 doesn't look very good. Let me rewrite that. Okay. 2, 3, 5 minus 0, 1, -4. And again, like before, I'll change this into plus 0, the -0 is 0, -1 plus 4. So what I get is x is equal to 2 plus 0 is 2, 3 minus 1 is 2, and 5 plus 4 is 9. Okay, that way I don't even have to sit down and say what are A, B, C, D, or, in this case it'd be A, B, and C, whatever. I'm just saying X is an entire matrix which is unknown to me, and now I'm solving for it. Cool. Alright, the next thing I would like to look at, and this is not what the book calls it, but I'm going to call it scalar multiplication. And this is the sort of simplest way that you can think about multiplying a matrix. And this is really just multiplying, I'm going to get rid of this quotes here because it's literally multiplying, multiplying by a constant. And let me just explain what you do via an example. So let's suppose I took 2 and I were to multiply that against the matrix 1, 0, -4, 3. You might have a guess as to what that should be. Well, what it works out to be is I just take 2 and I multiply that against everybody on the inside. 2 times -4, 2 times 3. What do I get? I get 2, 0, -8, and 6. Fantastic. So scalar multiplication is I just multiply by a constant, and there we go. I just multiply everybody on the inside. So generally, if I multiply the matrix X by a constant K, then the matrix K times X is X with all entries just multiplied by K. Now we've actually already seen this before in the context of Gauss-Jordan elimination. Let's consider the matrix a row matrix. So let's let X be the row matrix 1, 0, 3, 4, -2. This looks like maybe the first row of a matrix that we're trying to reduce. And let's let K be -2. Then K times X is -2 times 1, 0, 3, 4, -2. Why would I be doing this in the context of elimination? I'd be trying to get rid of, say, the number 2 below this one or something like that. And so we've already seen this before. When I multiply a row by -2, I just get each piece just multiplied by the number on the outside. 1 times -2, 0 times -2, 3 times -2, 4 times -2, -2 times -2, great, that gives us this. So we've already seen that before. I'm trying to think if there's really a lot more to say this. Why don't we just do one more example just for kicks? Let's evaluate -6 times the matrix 0, 1, 4, 2, 3, 0, 5, 6, -9, 0, 0, 2. And what does this give us? -6 times 0 gives me 0, -6 times 1 gives me -6, -6 times 4 gives me -24, -6 times 2 gives me -12, -6 times 3 gives me -18, -6 times 0 is 0, -6 times 5 is -30, -6 times 6 is -36, -6 times -9 is 54, -6 times 0 is 0, same thing here, -6 times 2 is -12, so this would be the answer. So multiplying by a constant, scalar multiplication is pretty simple. Let me just note the vocabulary is this. When I look at a constant times a matrix, it's the constant which is the scalar. So that's why it's called scalar multiplication. I'm multiplying the matrix X by a scalar. And it's called a scalar because it, in some sense, scales the matrix. If I multiply by 2, it somehow scales the matrix by a factor of 2. Cool. And do you just a little question, do you like my new tablet or palette or whatever you call it? Do you like it? I think it looks a lot nicer. I think I can read my handwriting a little bit better. I hope you can too.